getting the right medicine precisely where it needs to go in the body. I mean, that's one of the biggest challenges in modern medicine, isn't it?
It really is, especially when you think about major diseases like cancer. You mentioned it accounts for, what, 10 million deaths globally each year?
Sadly, yes. And the struggle isn't just finding a drug that works, it's delivering it effectively,
Yeah.
avoiding, collateral damage to healthy tissues.
Exactly. And that's where nanosystems, these tiny drug delivery systems, or DDS, really come into play. They can protect drugs, help them dissolve, cut down side effects.
But the ultimate goal, this sort of holy grail, is this theranostic idea, right?
That's the one. Therapy plus diagnostic, all rolled into a single nanoparticle. It treats the disease, and it tells you where it's going in real time.
So it's self-tracking while it does its job.
Precisely. And that's our mission for this deep dive. We're looking at some fascinating research on new, cost-effective mixed nanosystems designed to be inherently self-tracking.
Meaning no need for those extra fluorescent dyes people usually add.
Exactly. Those dyes can cause problems. They can leach out. They can fade, bleach over time. This work aims to build the tracking right into the nanoparticle itself.
Okay, so how do they do that? Let's get into the components. There are two key players being blended here.
That's right. First up, we have Polydiacetylenes, or PDAs, specifically a type called PCDA.
And what makes PCDA special?
Well, it's a conjugated polymer. Think of its structure as having alternating double and triple bonds, which creates this network of electrons. And that structure gives it really unique chromatic properties.
Chromatic properties,
Yeah.
meaning color. So this is the self-tracking part.
You got it. When PCDA is nicely ordered, sort of crystalline, it appears blue. And importantly, it's non-fluorescent in that state.
Okay.
But if it encounters a stimulus, maybe a certain temperature, or binds to a molecule, that orderly structure gets disturbed.
Ah, so the structure changes, and that makes the color change, like a tiny built-in sensor.
Exactly. It shifts pretty dramatically, actually, from that blue state to a red state. And this red form is weakly fluorescent.
So the particle itself signals where it is and what it's encountering just by changing color. No extra labels needed. That's clever.
It really is. It acts as its own sensor and imaging agent.
Okay, that's the PCDA. What's the second component? You mentioned PGA blends.
Right. Polyglycerol adipates, or PGA. These are polyesters. The big advantages here are that they're known to be biodegradable and very biocompatible, essential for anything going inside the body.
Makes sense.
And the researchers didn't just use standard PGA. They created specific versions, PGA-HX and PGA-BDM, by tuning their amphiphilicity.
Amphiphilicity. Okay, break that down for us non-chemists.
Fair enough. Think of it like having parts that like water and parts that like oil. Amphy means both. Getting that balance right is crucial for a nanoparticle.
Why is that?
Because our bodies are mostly water. Too much oil liking or hydrophobicity, and the particles clump up. Too much water liking, hydrophilic, and they might dissolve too fast or not hold onto the drug properly.
Okay, so tuning that property lets the nanoparticle behave correctly in the body and maybe helps it carry a drug.
Precisely. It helps it navigate the body's watery environment while still providing a good place to load, say, a hydrophobic drug.
So blending these two, PCDA for the color change tracking and PGA for the biocompatibility and structure, why not just try to make one super polymer that does everything? Why the blend?
That's a great question. Blending is actually a really attractive approach. It lets you combine different functionalities without having to go through incredibly complex chemical synthesis to build everything into one molecule.
Kind of a shortcut to getting multiple desired properties?
Sort of, yeah. A more practical route, maybe. Plus, it helps avoid those problems we talked about earlier, like the drug leaking out unexpectedly or the tracking dye fading away. It builds in robustness.
Got it. So how did they actually make these things? You mentioned the PGA synthesis was green.
Yes, they used an enzymatic synthesis route. And importantly, they used a solvent called 2-methyltetrahydrofuran.
And that's greener because...
It's derived from biomass from plant sources, not petrochemicals. So it's a much more sustainable way to make the polymer compared to using harsher traditional solvents.
Okay, that's a nice touch. So they make the PGA, they have the PCDA, and then they form the nanoparticles.
Right, using a fairly straightforward method called nanoprecipitation. And the resulting nanoparticles look really good.
How so?
They were nicely spherical, pretty uniform in size, what we call a narrow size distribution, and the sizes were right in the sweet spot, between about 115 and 284 nanometers.
Perfect for interacting with cells, I imagine.
Exactly. That size range is ideal.
Okay, let's circle back to that color change, the tracking system. We know PCDA does this blue to red shift with heat. How did blending it with PGA affect that? Did it make it more stable, less stable?
That was a really key part of the investigation. So first, you make the blue PCDA using UV light. It absorbs light around 640 nanometers. Then when you heat it, you get this shift, a hypsochromic shift towards the red phase, which peaks around 540 nanometers.
And the temperature needed for that shift, the activation point.
For the pure PCDA nanoparticles, that shift started happening around 40 degrees Celsius. We call it the onset temperature, or T onset.
40 degrees C, that's pretty close to body temperature, or at least a fever temperature.
Right. And that's where the blending made a huge difference. When they mixed the PCDA with the PGA variants, particularly PGA HX and PGA BDM, the T onset jumped significantly.
How much of it jumped?
Went up to 55 degrees Celsius.
Wow, okay, a 15-degree increase. Why is that jump to 55 degrees so important for using this inside the body?
Well, think about it. Normal body temp is 37 degrees C. If your sensor flips at 40, a slight fever, maybe some local inflammation, could trigger it prematurely.
Right, you might get a false signal or maybe even release a drug too early if it's linked.
Exactly. That 55-degree threshold means the system is much more thermally stable. It's robust enough to circulate in the body at normal temperatures without changing color unintentionally.
So it holds its state until it encounters a more specific higher temperature, like maybe in a targeted heated tumor.
Potentially, yes. Or it just means the tracking signal itself is stable during its journey. The researchers think this increased stability comes from interactions like hydrogen bonding and stacking between the polymer chains.
All right, so the engineering looks solid, the system is stable, it changes color predictably at a higher temperature. But the next big question is always, is it safe? How does it interact with living systems?
Crucial question. They started with in vitro tests using MCF7 human breast cancer cells.
And the results?
Pretty good, actually. Even at a fairly high concentrations, 250 micrograms per milliliter, the blended nanoparticles showed good cytocompatibility. Cell metabolic activity stayed above 90%.
So no immediate red flags for toxicity at the cellular level.
Right. Then they moved to an in vivo model, a living organism. They used the nematode worm, Caenorhabditis elegans.
Ah, C. elegans, a popular model. Good for reducing reliance on mammal testing, too.
Exactly. Follows the 3 R's principle. And this is where they stumbled upon something really, really interesting and important. It had to do with the solvent used to make the nanoparticles.
The solvent, not the nanoparticles themselves.
Correct. So when they formulated the nanoparticles using ethanol, which is generally considered safe, the worms were perfectly fine. Survival rates were near 100%, just like the controls.
Okay. But they tested another solvent.
They did. They also used DMSO, dimethyl sulfoxide, another very common lab solvent, and the results were drastically different.
How different?
When worms were exposed to nanoparticles made using DMSO, their viability plummeted. Only about 20 to 30% survived. A huge drop.
Wow. So it wasn't the PCDA or the PGA causing the problem.
Nope. They pinpointed the toxicity directly to residual DMSO left over from the formulation process. The polymers themselves seemed benign, but leftover solvent was highly toxic to the worms.
That's actually a massive point for actually making these things for real-world use, isn't it?
Absolutely massive. It underscores how critical the entire manufacturing process is, not just the final product's core components. Your fancy nanotechnology is only as safe as the harshest chemical used along the way. That's a major consideration for scale-up and regulation.
Okay, so using ethanol, the system was safe. Did the tracking part work in vivo? Could they actually see these nanoparticles inside the worms?
Yes, they could. Uptake was confirmed in both the cell cultures and the nematodes. And they found something interesting about particle size, too.
What was that?
In the MCF7 cells, the smaller particles, the PCD GAHX4 blend, around 116 nanometers, got into the cells much more efficiently than the slightly larger ones. Size really matters for cellular uptake.
Makes sense. And in the worms, could they see the red fluorescence?
They could. It was a great confirmation. They saw the red-emitting PCDA nanoparticles inside the C. elegans. In the younger larvae, the particles stayed mostly within the gut.
Okay.
But in the adult worms, they saw the nanoparticles not only in the gut lumen, but also inside the intestinal cells themselves.
So actual intracellular uptake and visualization, proof that the self-tracking works in a living organism without needing any external dyes.
Exactly. A really successful demonstration of the core concept.
One last piece on the biological side. Biodegradability. PCDA itself isn't biodegradable, you said.
That's right. PCDA is generally stable, but the PGA component is designed to be biodegradable. That's essential if you want the carrier system to be cleared from the body eventually.
So did they test if the PGA part breaks down?
They did. They used an enzyme, lipase, which is known to break down polyesters like PGA. They applied it to the PCD PGA-HEX4 blend.
And what happened?
It was quite dramatic visually. Within about 30 minutes, the nanoparticles started swelling up massively, going from around 300 nanometers to over 2,800 nanometers in diameter.
Whoa! Like they were falling apart.
Essentially, yes. After that rapid swelling, the nanoparticle structure collapsed. This showed the lipase was successfully interacting with and breaking down the PGHEX component.
So the biodegradable part works as intended, allowing the system to eventually disintegrate.
Correct. It confirms that the system has a built-in clearance mechanism, which is vital for any therapeutic application.
Okay, so we've got stable, self-tracking, biocompatible, and biodegradable nanoparticles. That ticks a lot of boxes. But the ultimate goal is diagnostic therapy and diagnosis. So can they actually carry a drug?
The crucial test. For this, they chose a drug called usnic acid, UA.
Usnic acid, what's special about that one?
It's got some interesting properties, anti-cancer, antimicrobial, but it has classic drug delivery problems. It's very hydrophobic, meaning it doesn't dissolve well in water, and it can be toxic to the liver.
So a prime candidate for needing an encapsulation system.
Exactly. It needs a carrier to be used safely and effectively.
So how did the nanoparticles fare? Let's start with the PCDA alone. Could its rigid structure hold much usnic acid?
Not really. As you might expect from that ordered, rigid structure, the pure PCDA nanoparticles showed very poor drug loading. The encapsulation efficiency, or EE, was less than 5%.
Okay, pretty dismal. Just not enough space or flexibility, I guess.
That's the thinking. The structure is just too tightly packed to easily accommodate the hydrophobic drug molecules being passively loaded in.
But the whole point of blending was to introduce that more flexible PGA component. Did the blended systems do better?
Oh, much, much better. This is where the blending strategy really shone. The PCDA-PGA4 blend managed to get up to 24% encapsulation efficiency.
That's a significant improvement.
It is, but the real star was the PCDA-PGA-TASX4 blend. That one reached an encapsulation efficiency of 30%.
30%. For a tricky drug like usnic acid, that's actually a really good result, isn't it?
It's a very promising result, yes. A huge improvement over PCDA alone.
So let's connect the dots back to the chemistry. What was it about the PGA-HEase variant that made it the best performer for drug loading? This is the aha moment, right?
It really is. It seems to come down to flexibility again, which in polymer science we often relate to the glass transition temperature, the TG.
The TG, remind us what that signifies.
You can think of it like the temperature where a rigid, glassy polymer becomes more rubbery and flexible, like comparing hard candy to chewy caramel. So the standard PGA they used has a TG around minus 28 degrees Celsius. Still below freezing, but relatively rigid in this context. The PGA-HX variant, however, has a much lower TG, way down at minus 50 Celsius.
So the PGA-HEX is inherently much more flexible, more rubbery, like a softer matrix.
Exactly. That lower TG means the polymer chains in the PGA-HEX blend have much more mobility. This creates a more flexible, dynamic environment within the nanoparticle.
And that flexibility allows the usnic acid molecules to wiggle their way in and find a stable place during formulation.
That's the interpretation. The softer, more amorphous matrix provided by PGA-HEX was simply better at accommodating and trapping the hydrophobic drug molecules. It shows how deliberately choosing the right blending polymer, tuning its properties like TG, directly impacts the drug-carrying capacity.
That's fantastic. It's a clear link between the specific chemical design and the practical functional outcome. So wrapping this up, what we've explored here is some really elegant work creating these novel blended nanosystems. You've got the PCDA providing the self-tracking color change.
Right, combined with biodegradable PGA variants.
And these blends are stable, much more stable thermally than PCDA alone. They're biocompatible, at least when made with the right solvent.
A crucial point, yes.
And they function as these cost-effective, self-tracking nanoparticles without needing any leachable dyes. Plus, the blending significantly boosted their ability to carry a challenging drug, hitting up to 30% efficiency with usnic acid in the PGA-HX blend.
It really pulls together a lot of desirable features into one platform. It strongly supports the feasibility of this blended approach for creating truly theranostic nanoparticles. They track themselves, and they can carry a payload.
Which brings us perfectly to our final provocative thought for you, our listener. We've seen these nanoparticles change color from blue to red based on temperature. That confirms the tracking works.
But what if you could engineer that color change to happen very specifically, only under certain conditions found, say, deep within a tumor? Maybe a precise temperature achieved by focus heating? Or perhaps a specific pH level that's unique to the cancer environment?
Then the platform could be more than just a passive tracker.
Exactly. Could that color change itself become the trigger? Could the shift from blue to red be engineered not just for visualization, but to actually initiate the release of the drug? Perhaps the structural change destabilizes the particle just enough.
Using the sensor mechanism as the release switch, fully integrating the diagnostic and therapeutic aspects.
That would unlock the ultimate theranostic potential. It's a fascinating possibility and definitely something for you to mull over or perhaps look into further on your own.